Right, what's going on, everybody? Today we're going to be doing find the duplicate number. So we're basically given an array of integers called nums. So in C++, that's a reference to a vector containing n plus 1 integers, where each integer is in the range 1 through n inclusive. So there's only one repeated number in nums, and they want us to return this repeated number. So, and we know this is the case. I think they ask this as a follow-up, like, how can we prove that at least one duplicate number must exist in nums? Well, if there's n plus one integers in this array, and they must be contained in the range one through n, like there's got to one of these has to be repeated, right? Because there's only like if these numbers, if we wanted these to all be x like what's the word, unique, like that would be impossible because we have to do that for n plus one different array elements, but we only have n options, so one of them has to be repeated. um so hopefully that makes sense. But they also don't want us to modify the array, right? So we're gonna have to do this in place, right? So we couldn't. So like one naive approach would be to like sort the array, right? And then after you sort, I mean, of course, it becomes n log n at that point. So it's gonna be worse time complexity than linear, but you would easily be able to just compare adjacent elements to see if there's duplicates. But we can't do that, right? Because we can't modify the array, and we need constant space. We can't copy it either. Um, we wouldn't be able to use a set. That'd be another easy linear time solution if you just used a set. But the problem with that is it uses linear space, right? And we can only use constant space. So it's like, so I mean, this problem is honestly like extremely difficult, right? I think um, so really the approach here is going to be to treat this array like it's a list. And we can actually use an algorithm called Floyd's cycle finding algorithm. You can look up more about that on the internet. There's like proofs for this algorithm. It's extremely clever. I think if you were to derive this on the spot in an interview, you're actually a genius, and you need to be doing something else. Like you should probably be doing research or something like this, or creating a startup or something. But nevertheless, yeah, let's just get into this problem. So like let's look at one of these example array inputs. So let's look at this example two. um, I think it's a pretty good example. So uh, I think it was, let's see, there were five elements: 3 1 3 4 2. So 3 1 3 4 2. Okay. And they basically want us to determine with constant space and linear runtime, right? Basically, which one of these numbers is repeated. So the way we're going to do this is we're going to look at the indices and the values to create a sort of linked list. We're not going to physically convert this to a linked list because we'd have to create like a struct for list nodes, and like we don't want to do that. So we're going to conceptualize this as a linked list, but we're not actually going to like physically convert it to one. And I'll show that how we're going to do that in the code once we get there. But let's just look at this like it's a list right now when we're uh, trying to visualize the algorithm. So this will be index 0. This will be index 1, index 2, index 3, and index 4 here. And then basically the way we're going to create our list is we're going to look at basically, um, we're going to start at the indices. We're going to see what index has what value, and then we're going to take the value at an index and then go to that value's index. So we would start at 0. So we'd have 0 here, and then it's like, where does 0 point to? Well, it points to 3. So we're gonna say 0 points to 3. And then what is 3 point to? Well, we're gonna look at the index for 3 here. That points to 4. So we have a 4 here. And then what is 4 point to? Well, that index points to 2. Okay, then what is 2 point to? That index points to 3. So we can see that's where our cycle is going to be. So, and there is always going to be a cycle here. That's like key to this algorithm. Notice we also have a 1 here. We can just, that would be like I forget what the terminology is for this in graph theory, but basically just have like a different disconnected graph here, another node that's by itself. Doesn't really matter for this algorithm, but this would be, you could imagine this floating somewhere off disconnected here. So regardless, so for our algorithm, we're going to do a slow pointer and a fast pointer. And just to give credit again, this is Floyd's cycle finding algorithm. You can look up the proofs for this online, but this is going to work every time. So um, we're going to have our fast pointer and we're going to move it forward by 2 nodes with each iteration. And we're going to move our slow pointer forward by 1 node with each iteration. And we're going to keep looping until these nodes intersect. So very similarly to the algorithm where we're finding a cycle in a linked list. So we're going to move the fast node by 2. So that'll be here, the first iteration. Slow pointer will be here. Okay, so that's after 1 iteration. Let's do it again. So fast pointer by 2. So 1, 2 for our fast pointer. And then we're going to move our slow pointer by 1 node, right? So that's where we would be next. And then we're going to do that again. And as you can see, fast pointer by 2, slow pointer by 1, those are going to be pointing to the same node now. So we know that we are somewhere within the cycle at this point because those nodes are now intersecting, meaning they are both pointing to the same list node. So once this happens, we're going to do the next part of the algorithm, right? Because notice the solution here is going to be 3, and that just so happens to be with this algorithm, it just so happens to be the beginning of the cycle, right? So we're basically just looking for the beginning of the cycle with the uh, list we just created, right? So for the next phase of the algorithm to find this node, we don't need our fast pointer anymore. So, but we do need the slow pointer. So we're going to take our fast pointer and set it back to the beginning of that list. So back to the array at index 0, pretty much. And we're going to keep basically incrementing both of these. We're going to have another loop now. We're going to keep incrementing the slow pointer and the fast pointer, this time by 1 node, both of them by 1 node. And it doesn't matter what this list looks like or how big the cycle is, how many nodes are before the cycle, we're always going to be able to move these forward by 1 node. And eventually, once they're intersecting, they will always intersect for the first time at the beginning of the cycle, and we can just return this node. So again, this is going to be called, let's I can't spell, but let's right. This is going to be called Floyd's cycle finding algo, right? So if you want to know the proofs for this, look it up more on the internet. I'm not going to go over it too much in this video because there's entire papers on this where there's really rigorous formulas and proofs where you can see that this is going to work every single time. But let's just get into the code because that's really what we care about here. So yeah, so let's get into the code. So basically, and it's not too long for this one, honestly. So again, we're not going to be actually like physically converting this a uh, to a linked list, because we don't want to have to deal with the structs and whatnot. So what we'll do is we'll just we can actually just traverse these arrays in that kind of list like manner just by indexing into them, right? And I'll show that. So we're gonna have a slow pointer that'll be 0 at first, right? Just pointing to that first index. And then we're going to also have a fast pointer, likewise, just pointing to the first 0th index there. We're going to basically just, we're going to loop while true. And we're just going to break out of this once like if our slow pointer is equal to our fast pointer, we can just break out of this first phase of the algorithm, right? Because remember, the first phase of the algorithm is just to get these fast and slow pointers. Remember, we were like here with our fast and our slow pointer, and at that point we knew we were somewhere in the cycle. We just didn't know where it started, right? So that's like the first phase of the algorithm. So that's what we're doing first. And kind of the trick here is going to be, remember to move our slow pointer forward by one. Well, how do we do that? We can just index into nums, accessing the index or the element at the slow index, right? That's kind of how we constructed our list from that vector. So we're going to move the slow pointer by one node like this. And then to move our fast pointer by two nodes, we're just going to index into nums twice, right? And that'll move the fast pointer forward by two nodes in this kind of list we're creating uh, here by indexing into our nums vector in this fashion. So this is the first part of the algorithm. At this point, slow and fast, we know there has to be a cycle, right? Because we discussed that, why that's true at the beginning of this video with these conditions or those constraints, problem constraints. So we know we're going to be in the cycle at this point somewhere. We don't know where, and slow and fast will be pointing to the same node, right? So for the next portion of the algorithm, right, we are going to recycle that fast pointer, right? Because remember, we didn't need it anymore. We're going to set that back to the beginning of the vector. So fast will be equal to 0 again. And then for this part of the algorithm, we're just going to loop while fast does not equal slow, right? And remember, if we just move these forward uh, by one node in that list, so if nums we do that by saying slow to nums slow, and then fast to nums fast. Like if we just move those four by one, they're eventually going to be pointing to the same node. And whenever they are, it's always going to be with Floyd's cycle finding algorithm, it's always going to be this first node here in the cycle. So we can literally just we can return either slow or fast. It wouldn't matter because those would both be pointing to that first node in the cycle. And remember, the first node in the cycle is always going to be the node that's repeated, right? So this is going to work every time. Um, so once again, this is going to be linear with respect to big O of n runtime, right? Because the number of iterations just depends on the however big this vector is, because it's going to directly affect the size of this list. And then the space is obviously just constant. So let's go ahead and run this and see how we did here. So beats 82% with runtime, 93% with memory. So pretty optimal solution. Hopefully this video helped you understand the problem more. If it did, please leave a like and subscribe, and I'll see you guys in the next piece.